Hello, and welcome to my commentary on Newton's second law. My name is Dean, and we will be going over case studies and application of Newton's second law. Now, to start off the presentation, let's look at what is Newton's second law. Now, Newton's second law stated concisely that force is equal to mass multiplied by acceleration. This is abbreviated with F is equal to ma. Now F of course being mass, F of course being force, m being mass, and a acceleration. Now we all know the units for each of the variables, but what is the unit for force? Now let's look at that equation again. F is equal to ma, m is kilograms, a is meters per second squared. So naturally, F is equal to kilograms multiplied by meter per second squared. Now this has a name associated with it. That name is Newton. And this is abbreviated as N. Since we have went over the basic equations for Newton's second law, let's look at our first example problem, titled Example Problem 1. Now, how much force is required to accelerate a 3 kilogram block of wood 1 meter per second square on a frictionless table? In order to solve the problem, we must assess what is given and what we are finding. Now, we are given mass and we are given displacement, acceleration rather, and we are finding force. Now, we know that F is equal to ma, and so this is pretty simple. Therefore, F is equal to 3 kilograms multiplied by 1 meter per second squared. And that is equal to 3 kilograms times meter per second squared. Or 3 Newton. Yay. Now, in order to move into a more complicated, more real-world applicable questions, we must look at what is friction. Now, friction is simply a force that directly opposes surface motion. Now, the reason I said surface motion is because a motion in air has air resistance, while a motion in a vacuum without any contact on the surface has no opposing force. Now, in order to better understand friction, let's visualize it a little bit. Take, for example, this blue box. Now, this blue box is moving to the right. This means that there is an opposing force called friction that is directly opposite of it. Now, let's discuss the types of friction. Now, there are static friction, and there's kinetic friction. Now, static friction is the amount of force that an object must overcome in order to indicate motion. It can be represented with this safe box because we are more accustomed to seeing a safe box at rest, and it has a very high static friction due to its mass. And kinetic friction. Kinetic friction is the frictional force associated with moving. So we would only be looking at kinetic friction in the example problems. This is because in all our example problems, the object is already moving or has started to move. Now, kinetic friction can be perceived as a cardboard box because we are accustomed to seeing it move. Now, in order to integrate friction into the equations of motion, Newton's second law, we must assess what is the coefficient of friction. It is abbreviated as mu, or that U symbol there. Its definition is the ratio of friction and normal force. In other words, mu is equal to F divided by F. Now, if we rearrange the equation, we find that normal force multiplied by mu is equal to friction. Now, normal force, of course, is equal to mass times gravity. The reason coefficient of friction is important is because it gives us the ratio of friction to normal force. So, whatever the object mass may be, as long as we know the coefficient of friction, we can find the amount of frictional force. Now that we know the equations of friction, let's move on to factoring in that into the equations of force. Now, the net force is equal to F applied, which is equal to mass times acceleration, minus friction, which is mu k times mass times gravity. Now that we know this formula, let's move on to our second example problem. How much force is required to accelerate a 3 kilogram block of 1 meter per second squared on a wooden table, given that the coefficient of kinetic friction is 0.6? Now again, let's assess what is given and what we are finding. We are given mass, we are given acceleration, and we are given the coefficient of friction. We are finding net force. Now we know that sigma F or F net is equal to F applied minus frictional force. And we know that, and if we rearrange that equation, we find that sigma F or net force plus friction, kinetic friction, is equal to F applied. And that's what we are finding. Now, kinetic friction is broken down into mu k multiplied by mass times gravity, which is mg. Now let's substitute all the numbers in. So net force is equal to 3 multiplied by 1, and mu k mg is equal to 0.6 multiplied by 3 multiplied by 9.81, and this is what we have. Now, we plug that into the calculator, we find that it is equal to 0.66 Newton, or 21 Newton. Did I say 0.66? I mean 20.66, which is equal to 21, 6 feet wide. Okay. Moving on to force operating on a slope. Now, in order to perform this calculation, we must first of all consider gravity, which is equal to mass times gravity multiplied by sine theta. And we also must consider friction. So this is equal to mu k sine theta. Now you might be wondering why we must use the sine theta cos theta. The reason for that is because we are at an angle, and therefore the forces of gravity doesn't act on the object as to the fullest of extent as it would if it was in a linear form. Okay, in order to understand this properly, let's look at it using this diagram. Now, there's an orange box which is moving down a ramp. This orange box has force of gravity acting on it. This vector is called h. Now, vector h can be resolved into two vectors, which is e. Now we are finding the angle between h and the vector that is parallel to the ramp. That we are finding the relationship between that angle and theta. Now, in order to see this more, look at it more conveniently, let's linearize this diagram. Let's extend vector h. Now once it's extended, we see that vector h makes a acute angle, a right angle to the ramp. And let's extend the resolved vector, and we see that using basic geometry, we know that that angle is equal to 90 minus theta. Therefore, since the two resolved vectors are 90 degrees away from one another, we know that this is theta. So, applying trigonometry, we find that the vector parallel to the ramp is equal to h multiplied by sine theta. Now that we know that, let's move on to our third example problem. Now, how much force is required to accelerate a 3 kilogram block of wood 1 meter per second square up a 30-degree wooden table to the horizontal, given that the coefficient of kinetic friction is 0.6. Again, let's assess what we are given, what we're finding. We're given mass, and we're given acceleration, we're given the coefficient of kinetic friction, and we're given the inclined angle. Now, we are finding net force, and so we know that sigma F, or net force, is equal to net force add with the force of friction, add with the force of gravity, is equal to F applied. Now we are finding F applied because we are finding how much force is needed to push a box up a ramp. Now that we know that Fk and Fg can be substituted by these equations, and by plugging in the numbers, we know that as follows. We get the answer as 26.5 newtons, which is 27 degrees, sigma wise. Yay! Now that we have finished my presentation, I would like to thank a couple of people before ending this presentation. Now, thank you, MacGregor, for providing me with a clip art of a safe box, and you can get that exact same safe box at the first link above. Thanks, Graphic River, for providing me with a clip art of a moving box. The guy who posted this clip art was moving. He took that picture of a moving block, and I took it from him. Yeah. Special thanks to Survey and Fawn for writing the physics textbook, in which I use to reference my information. Thank you. The end.